It's a special day today, last day of new content. So we will, for all intents and purposes, be done with the course content coverage. And today's actually should be fairly quick, as long as I don't overtalk it. So we're going to look at mean, variance, and standard deviation of which we did somewhere, 9.3 and 9.4 was looking at data. This time we're going to look at the mean, variance, and standard deviation for, what are these? Probability distributions, right? Probability distributions. So these are all going to be various probability. And what are the two rules a probability distribution has to follow? Two rules. What does the whole thing have to add to? That might be the easiest one. Can you have more than 100%? No, you can't. So 100, they have to, and you can't have less than 100. A probability distribution has to contain 100%. So actually, when we look at the function, it has to, the area under the curve has to add to 1, right? Which is 100. So that's one rule. The other thing is, can you have negative probabilities? No. So you can't have, for the original function, it dipping down below the x-axis. So those are the two rules. If it follows those two rules, then it's a probability distribution. Sum of under the curve is 1, and everything is, all of the things in that space is positive. It's a probability distribution. And then all this stuff is going to apply. What we're going to do now is look at what would be the average or the mean of that probability distribution. And this takes us back to calculus. However, the good news is you don't have to remember how to integrate so much. I mean, you can, but we can also do it with technology, because they're going to be looking for decimal equivalents and stuff. So you don't, in fact, one of the questions, student contacted me, they were putting in the exact values like we used to have to do, right? But this time they want the decimals. So the answer was correct, but they want the decimals now. Okay, so we'll get into that. But let's just go ahead and start in. And then on top of that, over the weekend, finish up this stuff, finish up homework as much as you can. That gets you into review mode. Again, you have until the final May 2nd to finish up any homework, but at least look over it, see what you know, what you don't know, try to do what you can, and get into that review mode so you're ready well in advance, okay? Because we have all next week to get questions answered. And Monday, I'll start off with the printed review, and I'll have some more stuff for you. So mean, variance, standard deviation. Most of this is just going to be screenshots from the PDF that I put in there for the P sections, the P appendices. There's a P1, P2, P3. So this is all coming from P3. And the first thing it says is that the mean of an expected value, if the expected value is a function, which I guess they all are, some function f, and it's defined going from A to B, whatever that is, and one of those could be infinity or both could be infinity. So whatever the length of that probability distribution is, to find the mean or the middle point, we take the integral. So this is expected value, which is expected value we end up calling the mean. And notice it's the function times the x variable. So it's just whatever that function is, you put it in your calculator, you multiply it by x, you graph it, and you get the integral. Oh, you're done. You got the mean. Okay, so it's a very nice place. And there's actually a couple ones we're going to look at that are even easier than that, if you remember. But if you don't remember those special little easy things, formulas, let me get this out of the way, this will always work as well. And we'll kind of do both. Say, okay, this works, but hey, there's this little thing where this is the constant, it's 1 over that, or something. It will work. So let's look at an example. We'll do this, and actually this is the one we'll look at. We're going to do it with that method, and then we're also going to show that there's a shortcut method that works just as well. So we talked about this earlier. We've got a troubled S&Ls, and they're failing at a continuous rate, and that's important. Continuous indicates that we're going to be using e to some power, because that's something like that. We've got a rate of 5% per year, but remember that's decreasing. So when you use the E as an exponential, the rate is up there, but since it's decreasing, it'll be a negative rate, negative 5%. Okay. And then we want to know how long will the average troubled SNL last? So on average, how long? So that's asking for the mean, the expected value. So the way we go about doing it, we kind of talked about this. I didn't give a lot of details, but if you want to go back, I think this was in P2. You can go back and they do give an explanation of how they came up with this formula, but it's just kind of, if there's an exponential decay, this rate, 5%, also appears in front. And again, it might just say, how does that happen? Well, you could watch through all the steps, and it does work out mathematically. For me, like being a business major, I say, I'll let those math people figure it out. And if they say it works, I'll believe them, right? Because they're not going to give me something that doesn't work. They've researched it. That's how we, that's how we make progress, right? We don't all have to develop AI, but we can use it to increase our speed at doing certain things. And there's tools out there that are doing that. I don't understand how it works. I'm never going to understand probably, but I can use them and I go, wow, did a PowerPoint put it into AI? Made it a little bit better. I reviewed it, but there's some tools out there that, hey, saved me probably hours of doing things. Okay, so back to the thing. So if we want to find the expected value, all we have to do is we take this integral, 0.5 e to the minus 0.05. Oh, sorry, that's 50%. 0.05. And notice the coefficient in front is positive where the exponent is negative. And again, it's explained if you follow through the steps, but that's just how it's going to be, because it will work out. And then there's an x up here, dx. And then the other part we need is this part right here. We're going to multiply this by x. So now this is not a probability distribution anymore. F of x is, but x times it is not. But x times it, if we integrate it, that area under the curve will give us the mean. Okay. And so how do we have to do this? Well, it doesn't make sense to go back negative years, because we're talking about they're failing now from some point. So we start at time 0. And this is a business thing where we don't know when the last one's going to do. So we use infinity, even though we don't go to infinity. That's the concept. So we're going to take this to infinity. And when we do it, we'll just think of infinity as a really big number. And again, if you look in the textbook, they go back to using limits, which we talked about in 210, but that might be like 6 months ago for some of you, or longer. So we don't have to talk about all that. What we're going to do is plug in our calculator. We use a big number, maybe 1,000, maybe 2,000, maybe 10,000, whatever. And again, that's the concept of limit. Just make it bigger until you get a number that fits, that, isn't just decimals. And that's all we got to do. Now we just need to plug it in. And we're going to have the mean. So this is how, see, we get to our calculator. Here we are. I'm going to turn this one off, right? I'll leave it in there, even though we're not going to use it today, and it's not too bad. But remember, that's the function you can use for the normal curve. So the stuff we do in chapter or P2, you could use that one. And I say, just go ahead and leave it in your calculator if you like, and even through the test. What was our function? It was x times 0.05 e, and the exponent was negative 0.05, and we had an x up there. So that's the function. That's going to give us the expected value. We're going to go to our graph, and we're going to use that calc function. And again, if you have a Casio, I've got to find, if you need help with this, let me know on a Casio. I don't know if I don't know right now, but I know how to find out how to do it on a Casio. Casios will do this. So what we do is we go to, but before we graph it, we've got to remember our limits are going from 0 to positive infinity, right? So I'm going to go to the window. That's the x value. So I'm going to make my x minimum 0 because I don't need anything below that. And I'm going to need my x maximum to go to infinity. I'll just put 1,500. You could put whatever you want, but let's just make it big. And usually this is big enough. If it's not, we'll make it a little bit bigger, and we'll see once we get there. My y values, usually because this is a probability distribution, we don't have to go up too high. I'm going to leave it. I've got a maximum of 0.5. I think that probably will be big enough. Let's see. Yeah. So this is going from 0 to 0.5 on the y, and notice it is big enough. Now remember, this is not a probability distribution. This is going to give us, because we're multiplying it by x. The probability x distribution, if we had it there and got the area under the curve, it would add to 1, right? Because it has to. But because we're multiplying by x, it's now when we get the area under the curve, it's going to give us the mean. Okay, so how do we do this? We go second, calc. We want to do this integration. And again, we could do this by hand, but if you do, the book will actually, there's an example that goes through here, uses integration by part. You have to remember all that. No, we don't. We just use our technology. Okay, so I do there. I'm going to start at 0. It says lower limit is 0. The upper limit, I'm going to make the far right, 1,500. If I went to 2,000, it would give me an error because it can't go beyond its window. So just know that you didn't do anything wrong. You just need to make a bigger window if you want to go out there. But I'm going to go all the way to the edge, 1,500, because that's what I set it to. It's going to give me, you see it's shaded it. It gave me the area under the curve, and it gives me the number 20. That's a nice solid number. No decimals or anything. I've gone far enough. You'll see if you maybe only went out to 100, it might give you 19.998 or something, so it would get you close. But remember the idea of limit, as you go further and further, it will eventually approach this particular limit. So this is telling us the answer is 20. Make sense? And that's all the problems you have to do. This will always give you, for a probability distribution, it will give you the mean. So we just return, and where are we? Here it is. And we say, oops, that this is our e to the x, which is expected value, and that equals 20. Now, on the next page, I'll show you the shortcut, but watch this. This one's really cool. If you recognize that it's an exponent, that it's this particular type of exponential, e to the minus some power, so it's decreasing, e to some minus power with the same rate in front. So 5% up in the rate, 5% in the front. These ones have a cool thing where the mean is just going to be 1 over this number. So 1 over 0.05. If you plug that into your calculator, you get 20. So if you remember the rule, it's even easier. Okay, 1 over 0.2, we got, it's just 20. We're done. So far, so good. You liking this? I did, because I thought, at first I looked, I go, man, this stuff is going to be, I remember doing this as a math major. This was a lot of work, because we had to do everything by hands and everything, and we didn't have graphing calculators back then, and had to walk to school in the snow and all that kind of stuff, Didn't have buses. No, we had buses. Okay, I'm not that old. Okay, so let's move on. So there are different types of means. So we're going to return to this one. So along with that, if we have an uniform distribution, what's a uniform distribution? It's like rolling a die. Every random variable has the same probability of happening. Rolling a die, that's all 1, 6, 1, 6, 1, 6. So that gives us a distribution that looks like this, going from A to B, and A to B could be, any numbers. And so doesn't it make sense that the mean in this case is going to be just halfway between those two? Half on one side, half on the other. Because that's really what the mean is, right? It's the half of not necessarily the median particularly is the middle number, but it's half of the stuff's below, half is going to be above as far as weighted. So there's this cool rule. You just take the two endpoints, add them together, and divide by 2, and that gets you to the middle. That's what the mean is. So and there's only one in the homework that has uniform, but so it's kind of one more thing to remember. But just part of it is, if you will remember what a uniform distribution is, it's just a box. It's a rectangle. Halfway, you're just finding the halfway point. If you remember that, that's what I tend to remember. Okay, that's the 2 points added together divided by 2. That always gives you the middle. Is that good? Again, I think I've got one in here. If not, we'll make one up. There is also this one that I just showed you. So we just did this. Again, as long as it's this form, a times e to the minus ax. Now, there's some in the homework that don't have that minus. It's e to maybe the 4x. You might have to work it a little differently. It's in the homework at the back, but I don't know if it's in the homework assignments. But this one only works if it's of this particular form. And actually, we're going to do a couple examples, and we'll see if it works out or not. But as long as you've got this, so you've got a negative here and a positive here, it's just 1 over a. That gives you your expected value. Okay, so we did that one. And there's only one more. And this one, there's not even any of these in the homework because it's just so simple. If it was a normal distribution, the mean is the mean. They're going to give it to us, right? So they didn't even give us any of this in the homework. But I put it here just to say, okay, normal distribution, what's the mean? Well, they gave it to us. They will tell us because that's part of a distribution, a normal distribution. Okay, so we don't really have to do anything. Now, what do we need? Remember, the mean gives us the middle. What's the other type of measurement we want with data? We also want the spread. So we calculate the variance, even though we don't really use the variance. We take the square root of the variance, and then we've got the square root, and that's what we use. So we do 2 calculations to get one number that we use. And so just think the square root, the standard deviation is what we'll use. But we need one more set of sort of formulas. Once I find the mean, how do we find the variance? Well, this is very similar to what we were doing before, right? We take each x value and subtract off the mean. So we had to find the mean first with these methods. So like that first example, we found the mean was 20. We would put in 20 for this, and we're going to do that as an example. But the cool part is we don't have to put each x, because what is x now? It's not a discrete random variable. It is a continuous random variable. So you can't just pick out 3, 4, 5. You got 3.5, you got 3.57, you got 3.578, or so you've got everything in between. That's why we're integrating. It actually makes it easier. Okay, so this is all that's added. So remember, when we find the mean, the calculation, what's going on here? Mean, M-E-A-N. The mean was this, x times f of x, going from A to B. And the variance is simply x minus that mean. So once you find it, so it's kind of like you find it and then you plug it in here. Okay. And then again, the standard deviation, all you do is once you've got that number, you take its square root and you've got that answer. Okay. Again, all this is using technology. It's all using technology. For a uniform, it's right there, uniform distribution. I just couldn't think. There is a special formula, and that's b minus a squared over 12. And again, you could look at the example in the book if you want to see why 12. I remember asking myself, but it's in the way they come up with so they go through the derivation of how they got to that, but it will always be the number 12. And you'll kind of see it's because of how the variance gets calculated with a uniform distribution. But for us, we're only going to have one problem. So why do we need to understand all this stuff to get one particular answer? And again, in reality, few things in this world that are real world are uniform distribution. Rolling dice, yes. Some, maybe if you're in a manufacturing situation, but usually there's some variance in there of some sort. So uniform is a type, but just remember, if you need its variance, b minus a squared over 12. So that's how we'll, and even as a math major, we looked at it, I didn't understand it, so we just use it and you get there. And then the exponential distribution also has an easy variance. It's, if you remember, it was 1 over a is our mean. The variance is just 1 over a squared. Okay, and that comes from the number's just going to be sitting here. So the main thing with an exponential is that you recognize it's an exponential distribution. You're going to be able to come up with the mean. It's 1 over this, 1 over a. The variance, 1 over a squared. And what's the standard deviation? 1 over a squared, the square root of 1 over a squared, which gets you back to the mean. But, oh, does it? Yeah, it sort of does. So, but I think with the uniform distribution, I think the question in the homework only asks you about the mean. I think that's, yeah, in fact, I'm sure. But you could calculate the variance and the standard deviation if needed. Okay, any questions? Good, let's do some examples and we're done. See, Little Crow's getting done in 30 minutes for the first time. So, but then I'll go over a little bit of a review of what you should start thinking about working on. But we're going to look at, I think I've got 3 examples for you. Here's one. See if that's big enough. That's function e to the x, and we're going from 0 to natural log of 2. So I'm going to kind of go a little slower through this. I'm going to actually show that e to the x dx going from 0 to the natural log of 2, I'm going to show that that equals 1. And then, because I want to show it is a probability distribution. Then we're going to find the mean, which is going to be x times the function. We'll find the mean. And we can do all this pretty quickly. And then we'll find the variance, which also is going to be fairly quick. Uh-oh, what did where's my calculator? There it is. In fact, well, yeah, I'll leave it this way. So let's get out of here. So this is just going to be e to the x. There. We're going from 0 to natural log of 2. Natural log of 2 is, I know, probably just need to go out not too far. So I'm going to go from 0 not to 1500, maybe out to 3. And I'll make my y maybe a little bit bigger. I'll just go to 1. I think that's enough. Maybe 2. Again, these are not real important. And you graph it, yeah, maybe I needed to go out a little bit. So this is what the function looks like. Now, it doesn't look like our standard one. It does, it's not a probability distribution if we go out to infinity, right? Because it keeps getting bigger. But what we can do is we're just proving to ourselves that this is a probability distribution. Now, the homework, you don't have to do that because by giving it to you, they're telling you it's a probability distribution. I just want to remind you, we take the integral going from 0 to the end limit, which was natural log of 2. And I think we might have done this in class under section 2. And we see that that area under that curve is 1. So we know it's a probability distribution. Okay, so that's a connection. They gave it to us, so we should be able to just assume it is. But we can do that. Second step, we're going to come back to find the mean. All we do is we change that function. I'm going to go second delete, which is INS, is insert. I can insert a value, so I don't have to retype it. I'm going to insert an x, And I'm going to insert a multiplication sign. I don't know if I have to. Oops. Well, maybe I shouldn't have done that. E to the x. I have to put this. Have to put that back in. So x times e to the x. When I integrate this, that's going to give me or give us the mean. Okay. So now we get the mean. We go back to our graph. It should work out. Notice the graph has changed because it is it's now a function that gives us the mean. It is not the probability distribution anymore because we're multiplying it by x. Kind of wanting you to think through that process. But we use the same limits, boundaries. We come to here, we're going to integrate from 0, lower bound, to natural log of 2, the upper bound. And this area does not have to be equal to 1. It might be a decimal. It might be something, and in this case, it's 0.3862. That is the mean. It's the average value of that distribution. Okay, so that will give us, so that's our answer, 0.3862. We come back there. Come back here. And so I'm going to put check that it's a probability distribution. Now, and you don't have to, again, you don't have to do that, but here's what we do: find the mean. Integrate from 0 to natural log of 2, x ex dx. And when we do that, we got 0. What was it? 3862. That's the mean. Now, they also want us to find the variance and the standard deviation. Standard deviation is just, once we've got the variance, we take its square root and we're done. So that's actually the easy part, getting the variance. Remember from the formulas, actually, my formulas are over here. I should have should have done this and this. But in fact, actually, let me get rid of this. Okay, so this is our mean. For our variance, we just have to remember we're going to take x minus that mean. Okay. And again, this is all recorded, so you can always go backwards, right? So for the variance, we're going to go from 0 to natural log of 2. But this time, we're going to do not just x times e to the x, we're going to do x minus that mean, which is 0.3862 squared. So that's always there, right? The same thing is happening right here. And then we put the function back in, which was just e to the x. Now, when we get this, that's going to give us our variance. And again, we don't actually have to integrate this by hand. That would be a mess, I think. Integration by parts and, but we just need the answer. What is the variance? We go to our calculator and we come and put this in. What I'm going to do is I'm going to delete these two things. I'm just going to put it on the back side. So I'm going to do a parentheses, which means times x minus 0.3862 squared. Remember to square it. That's all we have to do. We go again and find the integral. And the cool part about this is through the whole process, once we do on the first one, once we find a good window, it works pretty much for all of these. Now notice the function is different. It's not the probability distribution. It's not what we saw when we did the mean, because we're multiplying by x minus that. But this will give us the variance. And again, we do the same thing. We go second calc integral, and we take the integral from 0 to natural log of 2. And there's our variance, which is 0.0391. We'll round it to 4 decimal places. In the homework, they'll ask you to round it to 4 decimal places. That's our variance. But remember, it's tied to that calculation we did with the variance when we had data, x minus each piece. But because we're continuous, we get to do it with the integral. Actually, in some ways, continuous variables, they might be a little harder to understand because they can be all the decimals, but they're easier to work with in some ways. I don't have to calculate each one. So what's that? 0.0391. So we'll come back to this one. Let's put that in blue. So we get 0.0391 rounded, right? And then, so this is variance. And then the standard deviation is simply going to be the square root of 0.0391. So again, nothing much, just remember, standard deviation is always the square root of variance. We find the variance. My question was, why do we need the variance? So that we can get the standard deviation, but we don't use it really for anything else unless you get to more advanced statistics. And what it helps you find is sort of if you're doing a treatment, how much of the effect is due to the treatment. The variance can be used for that, but it's kind of advanced and it's very abstract. And I'm not a statistician, so I don't use it enough but I know they use it in those advanced stuff. What we use primarily in the less advanced stuff is a square root. So again, we just plug that in. And that one, you don't graph it or anything. You just come here and we find the square root of 0.0391. Now this was rounded. Occasionally I looked in the homework. I worked through a few and I got them wrong because I rounded at this point. Because they want it rounded to 4 decimal places, you might need to actually round it to 5 decimal places, the variance to 5 decimal places, so that the square root rounds accurately to 4 decimal places. Otherwise, you might be off on that last digit because we've already rounded, and so when we take the square root, we might get more rounding error. But for this case, I'm going to do this. But if your answer doesn't match, what I'll tell you is it's like this one I can see it's probably not going to make a difference because I've got a 1977 and then a 3. It probably wouldn't get rounded up. But there could be some rounding errors. Maybe that 7 really should be a 6 or something. So when you're doing the variance before, well, maybe I should, let's see if that happened. In the variance, what we had 3, I remember it was actually 0.03909. So going to 5 decimal places. Let's see if that makes any difference here. It may or may not. Square root of 0.0390. So that's 4 decimal places, 9. I saw that. I think we're going to be close enough with the rounding. It's still 0.1977. But notice in the 5th decimal place, it's only a 1, not a 3. So you could get it where that 3 might have been a 5, which you would have to round up, right? But you see that by using 5 decimal places on the variance, it gives you more accuracy. And again, I got one wrong, and then I looked it up. Oh, I'm just off on that last digit. It shouldn't have rounded up. So I used 5 decimal places, and you will always be correct. Sometimes it works, but it will always work with 5 decimal places on the variance. So just kind of keep that rule. Don't worry about it on the test. On the final, we're not going to get you off by 1,000, something in the thousandths place, but it might make a difference. Okay. So just to be as accurate as you want, for 4 decimal places, go to 5. So, and that's kind of a good rule in math, whatever you're doing. If you need to round to 4, have your calculations at least go out to the 5th place so that you can make sure that that rounding is working correctly. All right, we're almost there. So far making sense? Okay, so we're going to do 2 more. One more with the full sort of blown thing, and then one more simple one. Let's see. Let's go here. Okay, so we got, and that ended up being what? Was it what? 0.1977, regardless of how we round it. Yeah. So, and that's our standard deviation. So we would, again, if we're going to do things with it, we would use the mean, which was 0.3862, and the standard deviation, and then we can do stuff. But again, we're not applying. We don't have a chapter where we apply this, but if you needed to, that's generally what you would use. So this one, same thing. Now, the reason I put this one here is I just don't want you, because I was looking at this, oh, is that like that exponential and it's just going to be 1 over 4? But notice there's not a negative 4. If this had been a negative 4, then it would, but that would be 400%, right, in its growth. So this is not negative, so we can't use that simpler tool. So we use these same two things. And the other thing is it's going from negative infinity to 0. So how do we do that, right? So let's just kind of walk through this. We're going to do it all with technology. 4e to the 4x, going from negative infinity to 0. Again, just go back to our graphing tool. We're going to get this guy out of there. You could prove to yourself that it's a probability distribution, which it is. Again, you could graph it just with the function, go from negative infinity to 0. You'll see it's all equal to 1. I'm going to skip that step. What I'm going to graph is x times 4e to the 4x. So we're going to graph that going from negative infinity to 0. So we got to think about our window before we even go there. So our window, the x minimum has to be like negative infinity. Well, let's put in negative 2,000. That's way out. That's probably enough. Maybe. Our x maximum, 0, because that's the side we're working with. Our y values, 2 should be enough. I don't know, but we don't want to make it too big. We want to be able to see it, sort of. Actually, we don't have to see too much. So I'm just going to go ahead and graph it. Let's see. And you see, yeah, 2 was probably too much. You see a little, at least with mine, you'll see a red line. Yours, if you don't have color, you don't see much of anything because it's right above the x-axis, right? But watch, it's actually got some area there. We go second calc. We're going to do this. Now remember, the lower bound is negative infinity, and I set it up as negative 2,000, so that's what I'm going to use for my lower bound. Whatever you set the window at, that's what you use. And again, this is because we have to go to negative infinity. The upper bound, upper limit is 0. And this will give us I think I did have some problems with this one. What's that number? That's e to the minus 12, which is 10 to the negative 12, which means there's a bunch 0.0000. So that's basically 0. What did I do here? Make sure I got the right. So it was 4e to the 4x, right? Multiply it by x. We're trying to find the mean. It doesn't make sense that the mean would be 0. That would be the x value. It should be back a little bit. Let me try this. There was one that I went out too far and it starts sort of subtracting off or something. Let me only go to negative 500. Let's see. Let's go back to the graph. X is 0. Again, it's still way down there. But I remember I only went to 500. So negative 500 until 0. Let's see what we get this time. Yeah, we got a negative 0.25. Negative 0.25. The thing is these calculators, they use formulas to do these calculations. They don't actually draw the graphs and everything. So sometimes the technology, they didn't expect us to go to negative 2000, and what was happening is we're getting their calculation didn't work. But if we went to there, and I remember looking, this is the right answer. And that is 1/4, but it's negative 1/4. So you could maybe say, well, if it's positive, then the answer is going to be, then maybe the negative 4 would work. 1/4, right? It's 0.25, negative 0.2. But we could do it this way. So even though we're supposed to be able to go out to infinity, our calculator couldn't handle that calculation. But going out to about 500 was enough, and I don't see a bunch of digits. So remember, using limits, that's where I'm going to stop. Okay, so it's a little funky when we're using the technology, but because the technology is not perfect, it's not. Maybe you guys will help make it perfect in the future. And remember, these TI calculators, they've been around since before 2000. I mean, I started using, when I came back to teaching in the 1990s, I took a class on the TI 80, I think it was probably the 83 at that time, but they're 20 to 30 years old. And to make them backward compatible, they don't update them too much. They update some of the looks and stuff, but they keep, so that they can keep the old ones still active. Some things they're purposely not updating. Okay, so we so far so good. How do we find the variance? And then we just got one more and we'll be done. Kind of stretching it out here. Let's see. So we did this one, and we found that the mean e to the x was equal to negative 0.25, or if you wanted to think of that, could be negative 1/4. So you see how that we could still sort of use that rule, but it works a little different with that negative. So the variance, we might, so if you took this squared and took, maybe you could get the variance. But the other way to get the variance, right, is to take x minus the mean, which is negative 0.25. So it's going to be x plus 0.25 times the function e to the 4x dx. And again, we're going the same boundaries, negative infinity to 0. And that will give us the variance. And then we'll take the square root of that. And we'll just do that. And as you're doing the homework, it's kind of, you'll be able to do it with all this technology, just going back and forth here. Let's see. I'm going to insert parentheses. And I'm going to come here and I'm going to insert not that negative. I've got to subtract. Actually, it's going to be a plus, right? A negative. So I'll just put a plus to make it cleaner. That was what, 0.25? We'll go 0.25. Oops, I'm going to have to rewrite that anyway because I didn't. Squared. And then get down on the line times 4 e to the 4x. Okay, this is going to give us the variance just from the formula. So you'll do this enough times and it hopefully will stick because it's relatively the same. We use the same window. Remember, we're only going from negative 500 to 0 now. And again, we just use that same tool. We don't really see much, do we? If you wanted to see more, you could bring the y value down to maybe like 0.25 or something. But we're not going to see much because we're so far out to be able to get to negative infinity. So the lower limit's negative 500. The upper limit is 0. It does its work, and it tells us that the variance is 0.0625. And that's as accurate as we can get, 0.0625. And before, I don't want to go back and forth. Just keep that in your mind, 0.0625. So to get the standard deviation, square root 0.0625 gives us 0.25. And remember, I told you, I thought, that the standard deviation is going to be pretty much equal to the mean, except the mean was negative 0.25. You square that and then take its square root, you get positive 0.25. So those rules all work there. But again, if you just sort of follow these, you'll hopefully see some patterns that make it a little bit easier. So the variance was 0.0625, and then we took that square root, and that gave us 0.25, which is similar to the mean, but the mean was negative 0.25. Again, the mean can be negative, right? Actually, it should be negative because that's where it's at. And then on average, things deviate by 0.25. We good so far? And again, that's all you have to do in these. You just find them. Not much in the homework. And I think there was some in the homework about the median. I took them out because the median is really, that one kind of blew my mind too. There's a lot to it. And I says, if we're using a continuous random variable, we're going to be using the mean. You don't use the median. So anyway, it is there if you want to. Let me erase this stuff just to make it clear. And then this one, we're not even going to use a calculator. We're so good now, we can just use that method, right? So this one, it is a negative, so it does follow that pattern. What is the mean going to be? Well, I guess, oops, that's why I should have. We follow this rule if we remember this. Now, if we didn't remember this, we could go ahead and put it in there, x times it, and graph it, and get the integral underneath. Or we could just remember, oh, it's going to be 1 over a, the number in front. Yes? Yeah, as long as it's of that form, this will work. Notice this would have sort of worked on the one above, but it ended up being negative. And so that's kind of, sometimes I forget, if I try to remember too many things, well, if I got this exception, it works. So instead of memorizing that, I just say, I know as long as I've got the negative up here and a positive here, this is the rule. And this one, it sort of works on the others. And you'll do enough that it should hopefully make sense. And again, but if you don't remember the shortcut, it will work with the longhand by, plugging it in. And it's not that much longer, right? It's just put x times it and put it in the calculator. But all we have to do is, well, for us, that's going to be 1 over 0.02, which is 50, 100. Someone got a calculator ready? What is it? 1 over 0.02. Anyone got a calculator? I'm lazy right now, so. No? I think it's 100. 50. Yeah, maybe 50. Okay. 50 sounds about right. So if you take the reciprocal here, you should get about 50. And then I think I just wrote on where I have stuff appearing. So let me put it down here. 1 over 0.02 equals 50. The variance is 1 over a squared. So variance, I'm going to try to do this from memory. And then put it up there and say I didn't have to, but there's a shortcut for the variance too. But again, if I didn't remember that, I could use the one above. And that one is going to be 500 or 5,000 or something, or what is it? 0.02 squared, and then the reciprocal, 1 over 0.02 squared. I guess I could just pull it up. One divided by 0.02 squared. Oops, I don't need that. 2,500, 2,500, 2,500. And then remember, for the standard deviation, how do I get the standard deviation? Square root of the variance. And this should look familiar to you. I think we're going to get 50 square root of 2,500. And we do. So it's just with these exponential functions, the mean and the standard deviation are exactly the same, right? So we just go back. Oops, where are we? So that was the mean. The variance, which we don't ever really use, gives us that. And then the standard deviation is the square root of 2,500, which is 50. Okay, and I think that's the last. There is the standard deviation one, or the normal distribution, but there's none in the homework like that. It just makes sense, sort of. And then this is, yeah. Just remember, if you have, there is one question, and I remember it only asks for the mean of a uniform distribution. So you want to use this one. You just take the two endpoints and divide by 2. Okay, so that one, again, if you remember it visually, to me, I can remember pictures better than I can symbols, but it's just taking a box and you're going in halfway. So those are all the things you need to do for this. I think there's 6 or 7, maybe 8 questions at the most. There's not too many. I did take a couple out because I didn't want to go. It would basically be a whole nother day if we wanted to talk about how to find the median. But there is no use for the median when we've got a continuous random variable. And I know because my graduate math stuff, my attempt at graduate math, I was going to get a master's in mathematics itself in actuarial science, was probability. And we went through all that. When you get to continuous random variables, you're always going to use the mean. When you use the normal distribution, you always use the mean. You don't use the mean, even though the median's right there. So there was no real call for going through all this whole day lecture to figure out how to find the median, when as business majors, you're not going to use it. So anyway, there we go. So that will get you through random variables. And the reason we take you here, and it's very much mathematical, is that in your business situation, we want you to know that we a lot of times will assume a distribution is normal because there's a lot of tools and it's easier to work with. But there are instances when it's not normal. It's skewed one way or the other for various reasons. I want you to see for your business applications, if you see that the data is sort of skewed, it's not symmetrical, you know that there's another tool. You don't have to be the one to use the tool, but you know, hey, I got to call an expert. I know that there's a different way than using the normal. And if we use the normal, it's not going to work as well. In fact, we're going to probably be wrong. So I'm going to hire some expert to come and tell us what formula should we be using. Just that's mostly what this is about. So your experience is, you're not mathematicians, you're business majors, you're maybe marketing, you're admin, but you may need to see these tools. And maybe you're just the manager and you say, hey guys, and they're showing you all normal distributions. Did you consider that our data might be skewed? And they'll go, what? I don't know. Because they come through school and they just did the normal distribution, right? You know that there's other tools out there. That's what I want you to get out of this. And then you'll have great power in going forward. All right, and that's the end of the class. So next week will be just a quick overview. Let me get out of here just for a visual. You'll want to go, we'll keep them. We want to go, and again, we don't have to worry about going back to anything in chapter 1 or 2, although if you want to do some of that homework, it's available to you, and I'll pull the points over. It doesn't make, the tests are what really make the difference. So do what, get your stuff done so you're doing well on test 3, and the test 3 will be just over this content. Again, some of it does overlap with what we did, but we're not going to test you directly on what we did, just on what we're using in these sections. So there's this exam 3 review resources. Let's see what I got in there so far. I think I just have, not much, just the department review. And I'll start working some videos, get some solution videos for there. but just start working through that, and that will give you a good indication of the types of questions that'll be on the exam. We'll start reviewing on Monday. We've got Wednesday and we've got Friday. As I get more information about the final, I'll share it with you. How many questions, how many multiple choice, and this and that. And we will do it throughout the time. I will record class period. The lecture for this direct instruction might be shorter next week because I want you to be able to stay for those and work on things, ask questions. So because from now on, everything has been done. We're just going to come back and make the application and make sure that you understand and you're feeling confident and good. But I will record the first parts. But again, if you don't make it to class, you might not see, it might only be 5 or 10 minutes. We'll see if we run out of questions and then people are working individually. But that's what the goal is. And then just remember, after next week, we have finals week, and the following one, it's on Thursday night, May 2nd at 7:10 p.m. Which, again, because it's a common final. But the good news is we meet right here. So as long you don't have to go to a new place. Most have to go to a new place. We're right here. May 2nd, Thursday, 7:10 to 9, and we'll be good. And then that will be our finalist thing. So just time to start reviewing, practicing, getting it down. Let me know what you need. I'll work with you. I want to see you successful, because if you don't succeed, I don't succeed. I'm only successful if you're successful. So let's be successful together. Okay, awesome. Thank you.